Light does some of the strangest, most spectacular things in the universe. And one of the most mind-bending examples is something astronomers call light echo. One may think it is something like sound bouncing off a canyon wall, but what it actually describes is a phenomena so visually dramatic that it can look like the universe is breaking its own rules. Imagine a star in the darkness of space that suddenly flashes like an astronomical flashbulb, either in a catastrophic explosion like a supernova or in a sudden burst of brightness 1,000 times stronger than normal. The single burst of light races outward in all directions, illuminating the dust and gas around the star. And from Earth, what we sometimes see is an expanding bubble or ring of glowing material that appeared to grow outward far faster than the speed of light itself. But how is that possible? Special relativity tells us with almost sacred authority that nothing can travel faster than light. Yet, here we are, watching something expand across space at what seems like superluminal speed. But here our intuition, our everyday sense of how light should behave fails us completely. Because what we think we are seeing is not what is actually happening. The glowing bubble is not a physical shell racing outward. No dust is being hurled away at impossible velocities. Instead, what we are witnessing is geometry, time, and the finite speed of light combining to create an illusion that feels like a paradox. At each instant after the flash, we only see dust grains that happen to be in exactly the right place so that the travel time of the light works out perfectly. First from the star to the dust, and then from the dust to us on Earth. That condition defines a very specific three-dimensional shape in space, an ellipsoid. The surface where the sum of distance of two focal points is constant. One focus is the exploding star, the other focus is Earth. So at any given moment, the light we see is reflected from dust grains lying on the surface of a vast, stretched ellipsoid sweeping through space. And because that surface can intersect distant dust clouds that project as rapidly expanding rings, it can appear to grow faster than light, even though nothing physically is actually outrunning light. It's like shining a laser pointer across the moon. The spot can sweep across the lunar surface faster than light, without any object actually moving that fast. Light echoes are the universe doing something similar, but on a scale of light years. The first time astronomers truly recognized this phenomena was around nova outbursts, massive nuclear explosions that occur when a dense stellar remnant, a white dwarf, steals too much hydrogen from a companion star. These events can brighten a star system enormously, producing the perfect flash to illuminate surrounding dust. The mathematics behind light echoes was worked out in detail by French astronomer Paul Koderk, a scientist known for not only his research but also for his passion for explaining relativity to the public. In a 1939 paper that is still cited today, Koderk explained the strange expanding rings photographed around Nova Persei 1901. Each ring was an intersection of interstellar dust clouds with that ellipsoidal surface of equal light travel time, and the rings could appear to expand much faster than light, which seems shocking until you realize what is moving is not matter, but the location in space from which light happens to be arriving at the correct moment. Light echoes don't violate relativity because relativity is about motion of objects and information. The echo is neither an object nor information traveling faster than light. It's simply the geometry of when scattered light reaches our eyes. The phenomena became spectacularly famous in the aftermath of one of the most important astronomical events of the 20th century, supernova 1987A. In February of 1987, a star exploded in the Large Magellanic Cloud, one of Milky Way's satellite galaxies, about 160,000 light-years away. This galaxy lies so far south in the sky that only observers below the latitude of Mexico City can see it at all. On February 23, 1987, the supernova became visible to the naked eye, the first such event since 1604, when, by the way, Galileo was still alive. The formal discovery was made by Ian Shelton, an observing assistant at Cerro Las Campanas in Chile, who was testing an old wide field lens system by photographing the Large Magellanic Cloud. When he developed the photographic plate, he noticed a bright new star near the center. Almost simultaneously, Oscar Duhamel, taking a break from operating a large telescope, saw it visually. Soon, the astronomers at the site stepped outside to witness something that almost no human being ever sees: the sudden appearance of a supernova in the sky. Communicating this discovery to the world was not as simple as sending an email. This was 1987 after all. They contacted the International Astronomical Union's Central Bureau for Astronomical Telegrams at Harvard, and confirmation came quickly from New Zealand. Other observers later realized that they had unknowingly photographed the supernova's initial brightness the night before, and some saw it but could not report it for days. But what mattered was that humanity had caught a nearby stellar death in real time. Supernova 1987A was extraordinary because it occurred in a galaxy that had been closely studied as a laboratory for stellar evolution. For the first time, astronomers actually knew something about the star because it exploded. It was a brilliant blue star, catalogued as Sandulek 69202, sitting near the Tarantula Nebula, a vast star-forming region. The explosion was also detected by neutrino observatories built to monitor the sun, offering deep insight into the core collapse process. But visually, one of the most haunting results came later, as the supernova faded. The dying star shone as bright as the North Star for weeks, then gradually dimmed, revealing its surroundings. And those surroundings contained rapidly expanding rings, light echoes. These rings offered a unique opportunity because each echo marked where the ellipsoid of arriving light intersected dust sheets. Astronomers could map the distribution of the dust in the Large Magellanic Cloud in 3 dimensions. Over 16 years of observations, researchers combined echo data to reconstruct the star's environment. They found that the star's influence extended far beyond the glowing hourglass nebula seen in standard images. Long before the final explosion, the star had been blowing powerful winds through multiple phases of its life, sculpting a vast peanut-shaped cloud of gas and dust stretching 28 light years along its poles and 11 light years near the equator. The bright rings in typical images were only about 1 to 1.3 light years from the star. Most of the star's earlier mass loss was invisible until the final flash briefly lit it up, revealing the ghostly record of its life. It may seem strange that dust so far away from the explosion could reflect the light so brightly, but the secret lies in the nature of interstellar dust itself. These particles are incredibly tiny, almost all smaller than a quarter of a micron, less than 0.00025 millimeters. Particles that small scatter light forward very efficiently, deflecting it only slightly, a process called forward scattering. This means that most of supernova's light bounces off the dust grains at only a few degrees from its original direction. As a result, the dust that is easiest for us to see is dust lying almost directly in front of the supernova along our line of sight. This is also why when we see blue starlight scattered around the Pleiades star cluster, we are mostly seeing the dust on the front side. Our everyday intuition is shaped by large objects, but the universe operates on microscopic grains and behaves more like fog in headlight than like mirror shards. Light echoes, therefore, become excellent probes for the dust between us and the bright transient events. The light echoes are not limited to supernova. In January of 2002, a star called V838 Monocerotis suddenly brightened by a factor of 10,000. Over 6 weeks, it changed brightness and color in a way that didn't match any known type of variable star or typical nova eruption. Ground-based telescopes soon noticed a faint fuzzy patch expanding around it, so rapidly that it could only be a light echo. Then the Hubble took over. In a spectacular series of images led by Howard Bond, the expanding echo was traced over 2 years as light illuminated dusty shells and cavities around the star. Here the time dimension breaks the flatness of the picture. Each dust patch tags itself with distance along our line of sight because it lights up at a specific delay. Each echo revealed thick shells of dust centered on the star, evidence of previous outbursts thousands of years ago. It even revealed the star's true distance. Despite appearing against a nearby spiral arm region, V838 Monocerotis was actually isolated in the outer disk of the Milky Way, 20,000 light-years from Earth. Light echoes act as diagnostic tools, cosmic CT scans of stellar neighborhoods. Even less violent stars can produce echoes. The Cepheid variable RS Puppis is surrounded by so much dust that it has a permanent set of light echoes. As the star pulsates every 41 days, different dust regions brighten and dim with different phases depending on their light travel time. The echoes become a 3-dimensional rhythm, a delayed chorus of scattered light, and then the universe gets even stranger because sometimes the opposite happens, not light echoes but something like dark echoes. Some young stars are so heavily shrouded in dust that you only see their light after it scatters off surrounding clouds. Some of these nebula are remarkably variable, changing brightness and shapes from year to year. One famous example is NGC 2261, known as Hubble's Variable Nebula. The change could not be physical motion of gas that would require faster than light speed. Instead, the illumination changes. We are seeing shadows cast by dusty patches near the hidden star R Monocerotis, projected outwards like cosmic searchlight beams. Similarly, dark echoes appear around UW Centauri, a rare star where carbon soot clouds condense and temporarily block the star's light. Between these absorbing patches, beams of light shine outward, letting astronomers trace events occurring too close to resolve directly. Light echoes can even be detected when they are too distant to separate visually. Some distant supernova show slight brightening long after the explosion, consistent with the echoes from nearby dust. But perhaps their most profound application has been in probing quasars and active galactic nuclei, the brightest individual sources in the universe. One of the earliest surprises about quasars was that they flicker in brightness from week to week, and in X-rays sometimes within minutes. That flickering reveals something astonishing. The emitting region must be extremely small, because no object can change brightness faster than light can cross it. A galaxy-sized source cannot flicker in minutes. The speed of light imposes not only a limit on motion but a limit on how fast information and change can propagate across an object. If the sun were switched off instantly, we would not see it vanish all at once. The darkness would spread across its disk over about 2 seconds, because light from the edges takes longer to reach us than light from the center. The finite speed of light smears out reality, enforcing causality even in the act of seeing. So light echoes, in the end, are one of the most spectacular demonstrations that the universe is not obligated to match our intuition. They show how time and geometry shape what we observe, how apparent motion can be faster than light without any physical violation, and how dust, tiny grains floating between stars, can become the screens onto which cosmic events are projected. A supernova's flash does not just mark a death, it briefly reveals the hidden structure of space around it, lighting up the fossil records of stellar winds and past outbursts. Light echoes remind us that seeing is not instantaneous, that the universe is always delayed, always layered in time, and sometimes what looks like something impossible, something outrunning light, is actually the universe showing us in the most dramatic way possible that the speed of light is not just a number, it is the rule that shapes the very way reality unfolds before our eyes.